Hey guys, welcome back. We're going to continue chapter 14 with the second part, really honing in on independence. So in this one, we're going to be looking at the relationship between academic performance and sex. So these are actually going to be data from my students last year because this year our semester grades aren't necessarily finalized yet, so I don't really necessarily know what to do for that. So I'm just going to use the data from last year anyway. All right, so our conditional probability is the probability of B occurring given that A has already happened. So that's red, the probability of B given A. So that's how you read it. That's what the line means there. So it looks like from last year, 72% of my stat students were female. 38% of all my students ended the first semester with an A or a B. So you can kind of compare how we're doing this year. Clearly probably not as good because of all the craziness, but anyway, and then 30% were female that had an A or a B. So you can fill in the disjoint probabilities is probably the first thing I would do. So what percent are female that did not have an A or a B? So 72 minus 30% would give me 42%, and then 38 minus 30 would give me 8%. So there were 8% that had an A or B that were not females. So those were the males with A's and B's. And then on the outside would be, if I added all these together, I'm going to do the 78 for the female plus the 8% for the male, which would give me 80%, meaning there were 20% that were made up of males that did not have A's or B's. And that's out of the entire 100, out of all the students. So those are all your disjoint probabilities. So those four, these are the marginal distributions, marginal probability for female and for A and B's. Part B, we want to find the probability that the student got an A or B given that it was a female. So we're only interested in the set of all of the females, which in this case would be the 72%. So out of the 72%, which is the percent of my students were female last year, of course, then what percent of those had an A or a B? Well, that would be the intersection of those two, right? Which would be the 30%. So it's going to be 30% out of the 72%, which when I put that in the calculator gives me 41.7%. So 41.7% of all my females last year had an A or a B in my class. Now, if we're going to compare that to the conditional distribution for the males, that would be an easy way to decide whether or not these are going to be independent, right? Were the males more or less likely to have an A or a B in my class than the females were? So what about for the males? So out of the 28%, which is the males, we had 8%, which had A's or B's. So 8% out of 28 was only 28.6%. So clearly looking at the difference between these two, this is one way you can compare the conditional distributions to see if they were actually independent. Just like the Titanic, right? We would expect all the classes to have the same survival rate. And if sex was independent of grades, then we would expect the male and females to have the same conditional probability of having an A or B in my class from last year. But they're not. There's about a 10% difference. So the females outperform the males. Keep in mind, it's a fairly small sample size, so just the difference of like 2 students could have changed that. So it's not necessarily statistically significant. So find the probability that was a female given that they had an A or B. So out of the A or B's, which is now 38%, that's our new denominator, what's the probability it was a female? So we need to know the intersection that were female and A or B, which was the 30%. So that would be 30% out of the 38, which would be altogether a 78.9%. So if you told me that you had an A or B last semester, then there's a 78.9% that person that told me that was female. Which means they made up 78.9% of all the people with A's or B's. They also were a majority of my students. 72% of all my students last year were female. All right, moving on. All right, so then we're going to look specifically at independence. So you can compare 2 conditional probabilities, but the best way to compare for independence is to compare one of the conditional probabilities to a marginal distribution or marginal probability. So the overall probability of having an A or B from last year was 38%. And we compare that to the conditional for the female, which we've already done, by the way, which was the 41.7%. And are those two the same? They're not exactly the same, but they're really close. The next question is, are they close enough for us to believe that they might be independent? Is there strong evidence? Well, those are pretty close, so probably wouldn't say there was strong evidence. There might be some or weak evidence of an association between the two. So do grades seem independent of sex? It depends on your interpretation. There's certainly not strong evidence of an association between the two. So I would say there was either weak or yeah, probably weak evidence of an association. Probably be the best way to say it. All right, so what's an alternative method for testing for independence? Well, you can actually use a multiplication rule. So if these two were independent, then 38% of the 72% of the females would be both, right? So what's 38% of 72? Let me pull up my calculator, or 72% of 38. So 0.38 times 0.72, which will be 27.36. So that's a percent that we would expect using our multiplication rule if they were actually independent of each other. I don't know why I like to do that. Okay, so we would expect this to be 27.4%. What's essentially going on here is we ask ourselves how, let me try that again. I guess I'll do that on the next one, but it should be 27.4%. And what percent did we have? We had 30%. Well, is that significantly different? Not necessarily. Again, weak evidence of an association. All right, so graphically speaking here, we kind of looked at this yesterday. These were the goals for the boys and the girls, the 4th, 5th, and 6th graders, I believe, from Michigan. So if we have our marginal distribution overall, we're going to look at grades here. So what percent overall thought grades were most important? Well, the marginal is going to be, for grades, 247 out of the 478, which is 51.1 or 51.7%. What about the conditional for the boys? Well, conditional for the boys would be 117 out of 227, which is really, really close. And then we could compare it to the conditional for the females, which would be 130 out of 251, which again is really, really close. These are all so very close that there's really no evidence of an association, at least for the grades. But if we have more than one variable, we actually need to check the other ones as well, because there clearly was an association between popularity and sports. But grades, there was no evidence of an association. So again, what are we doing? We're comparing a marginal distribution like we had here, the overall for grades, to one of the conditionals to see if there was a difference. All right, so disjoint and independence, they're completely different things. So let's see if we can kind of break that down. So if two events are disjoint, then knowing that one of them happens makes it impossible for the other to happen because there's no overlap. That is far from independence, which leaves the probabilities unchanged. So independent, they have to overlap. The mutually exclusive ones, they can't overlap. So probability of having an A last year was 22% of my students had A's, 16% had B's. Well, you can't have an A and a B, so these two actually should be mutually exclusive, right? There's no intersection between those two. It's an empty set. The intersection is empty. But when it comes to female and A or B, certainly there were females that had A's and B's. Those are not those are not mutually exclusive events. The only question is whether or not they're independent. And their independence is going to be basically how much of an intersection did we have between those two? Was it more than what we'd expect, more than 72% of 38 or 38% of 72? Or was it less? Was there even less than what we would have expected? In our case, there was maybe slightly more than what we would have expected, which would be like 27%, and we actually had 30%. Okay, are A and B and being female mutually exclusive? So are those two mutually exclusive? No, because their intersection is not empty, right? There was 30% that were both female and had A or B. Certainly, there were some of my students that had A's and B's that were females. All right, so the general multiplication rule says that for any two events, A and B, the probability of A and B occurring is the probability of A times the probability of B, given that A has already happened. So that's the conditional probability. So our first event times the conditional, which will give you the overall intersection of the two. Now this is a general multiplication rule because it takes into account the fact that A had already happened. So they don't have to be independent because we know what the conditional probability is of B occurring given A had already happened. You can do the same with probability B times the probability of A given B happens, so it doesn't really matter the order. Now this is most clearly shown with a tree diagram. So for instance, the first event is the probability that you were female or male. So I've kind of broken this down. I think I like it better when I put the male one down here, but that way it's kind of broken off a little bit. So 72% were female, 28% were male. That's the probability of the sex. And then after that, the second one is the conditional probability. given whatever branch we're on. So if you were a female, the probability that you had an A or B was 42%. The probability that you did not have an A or B, which would be a C or below, would be 58%. Now those are the conditional probabilities. I had to calculate those separately, right? So that would be, of the 72% probability that you had A or B was 58 or 38. So 38 out of 72, that's where we got the 42. And what was left over would be what had to be the probability that you did not have an A or B, which would be the remaining portion, 42%, divided by the 72%, which would be 58%. Okay, then whenever you multiply these together, that's what gives us our disjoint probabilities, which are the ones that were only female, female with A or B, or male with A or B, or male without A and B. Those are these disjoint probabilities at the end. And we actually multiply just the first event, probability of being female, it's being on the first branch, times the next one, probability of having A or B, to give us the overall probability of 30%. It kind of comes out of the wash whenever you multiply those together. Same thing with male, 28% were male, and then to get the percent of A's and B's, that would be 8% out of 28%, which was 29, meaning the complement of that 71% had to be not. And then you multiply 28 times 29%, which will give you 8%, which is what we had here. And then the same thing for the 20% when you multiply those two. It just kind of undoes what we just did. So kind of cool. And then the last thing I want to point out is that the sum of all the disjoint probabilities has to add up to 1. In this case, because there's 2 events, there's 4 disjoint probabilities, only female, female with an A or B, male with an A or B, or male without an A or B. And that's it. So pretty cool. All right, drawing without replacement. Anytime we draw, whenever we like flip a coin or roll a dice, it always resets. So there's no drawing without replacement. But anytime that we draw from a deck and we don't replace the cards and then shuffle it, shuffle 7 times, the probabilities are going to change. So for instance, if we're trying to find the probability of drawing a 9, well, how many 9s are there in the whole deck? There's going to be 4 of them, and 4 out of the whole deck of 52 cards. But after that first draw, and I've already, let's say I drew a 9, the probabilities are going to change, right? Now there's only 3 remaining out of 51. So the probabilities are not consistent, knowing that whatever happened in the first card, whether it was a 9 or not, that's going to change the probability of drawing a 9 on the second card. So, because even the denominator would change, even if the numerator stayed the same. So, in case you're curious, that is a probability of drawing a 9, 2 9s in a row, which would be really, really rare. All right, example 1. So suppose 25% of people have a dog, 29% have a cat. So this is the same one we did yesterday. Now the only thing that's different is we're going to look at specifically conditional probabilities and see if they're mutually exclusive or independent. So if someone had a dog, I guess we can fill in this information, which we kind of already knew. If someone has a dog, what's the probability they have a cat as well? So what's the probability they have a cat given that we know they have a dog? Well, what percent had dogs? That was a 25%. You can see the marginal distribution that's straddling the line. And out of those, looks like 12%. So we're looking at 12 out of 25%, which would be a total of 48%. So if you have a dog, the probability you have a cat as well is 48%. So are those independent? Well, I already have a conditional probability of cat given dog. I need to compare that to the overall marginal probability of cats, and that having a cat, which was 29%. So is 29% the same as 48? No, it's about 2/3 of that, right? And so your likelihood of having a cat if you own a dog actually goes up from 29% for the general population to 48% for those who have dogs. So they're not independent, because overall probability of having cats 29%, which is not equal to 48%, which was the probability of having a cat given that you had a dog. This is a nice string that you can do here with the equality or inequality in the middle. It's nice, easy to read, just kind of going from one all the way to the other. You could say it in a sentence, but this is really good. If you write down on a test, I'd be very happy. All right, so are having a dog and a cat mutually exclusive? No, because the probability of having a cat and a dog is 12%, which is not equal to 0. It's not empty set. All right, number 30. 56% of all American workers have workplace retirement plans. So 56% is the marginal. 68 have a health insurance, and then 49% have both. So if we subtract, that'll give us a difference of 7% that only have retirement but no health insurance. And then if we subtract these two, that'll give us 19% that have health insurance but not retirement. So there's our Venn diagram. We could add those together, subtract from 1 to get the part on the outside if we were interested, which I guess we are. So what's the probability they have neither of them? All right, so I'm going to add these together. So 7% plus 49% plus 19%, and subtract it from 1, which leaves me with 25% on the outside. probability that they have health insurance if they have a retirement plan. So out of the people who have a retirement plan, which is the marginal distribution of 56, what percent of those had health insurance as well? So it would be the 49%, which are both, out of the 56, which will be really high, 0.875%. Are health insurance and retirement plan independent events? Well, we need to compare a conditional to a marginal. We already have our conditional here. So this is the probability of health given retirement. So what's the overall probability of health, which is 68%? Is that the same as the 87.5? No, they're not. So they are not independent events because the conditional probability of health given retirement is higher than the probability of just the health. So knowing that you have a retirement plan increases your likelihood of having a health insurance plan by about 20% there. All right, so are having two benefits mutually exclusive? Again, no, because you can have both. In fact, the intersection of two is equal to 49%, which is not equal to 0. So they overlap, right? People have retirement and health insurance. All right, the soccer team shirts have arrived in the big box, and people just started grabbing them, looking for the right size. The box contains 4 medium, so I'm just going to fill it in here, 10 large, and 6 extra large. Notice that you can't have a medium large. They're going to be mutually exclusive, so I'm drawing them with no intersection, no overlap, and there weren't any other sizes given other than that, so you could put a 0 on the outside if you wanted to. So altogether, there are 20 shirts. You'll need to know that. All right, what's the probability the first you grab are the wrong sizes? You want to grab a medium for you and for your sister. So we're looking for a medium. So what's the probability the first two are not mediums? Well, there's only 4 mediums. There's 16 that are not. So it'd be 16 out of 20. And then after you grabbed one of them that was wrong, what's the probability the next one you grab is wrong as well? It depends if you put it back. They didn't actually specify a replacement. I guess, so if you didn't replace it, it would be 15 out of 19. Because we took the second one out. In fact, it would make sense. It would be better for you to not put it back in there because you could then grab the same shirt twice, right? So we'll assume that we didn't replace it. But if you saw it how it was the wrong size and you threw it back, then you're actually not helping yourself out technically. Statistically speaking, it's kind of fun. All right, so multiply those. We're going to put those in the calculator. I kind of showed you how to do that yesterday. Let me do it again. So do alpha x, and in the numerator we're doing 16 times 15, and the denominator we'll do 20 times 19. And then we need to convert this to a decimal. So we're going to go to math, and the second option, which will convert to a decimal, and I'll give it 63%. All right. The first medium you find is the third one. So if the first medium you find is the third one, means the first two had to be not a medium, which is the same probability we just did, by the way. The only difference is now we're multiplying that by the third one being a medium, which was 4 out of the remaining 18 shirts. Again, assuming that we didn't put them back. So I'm going to take my previous answer and just simply multiply it by 4 and divide it by 18, which will give us 14%. So that's a very specific outcome of finding the first medium on the third shirt that you drew without replacement. The first 4 shirts you pick are all extra large. So the probability of the first one being extra large is out of 20 shirts, we have 6 that were extra large. Then after we picked one of them that was extra large, the next one there's only 5 remaining out of 19. And then after that there's only 4 out of 18 remaining, and then only 3 extra large out of 17 remaining. So when we put this in the calculator, we'll do alpha x again, and I'm going to do in the numerator 6, oops, I mean do that, 6 times 5 times 4 times 3, and then the denominator 20 times 19 times 18 times 17. Alright, then I want to change that to a decimal, which is only like 3%. Okay, so that's really rare that you would pick 4 extra large in a row. All right, at least one of the first 4 shirts you pick is a medium, so at least you get at least one of the mediums you were looking for out of the first 4 that you pick out of the box. So anytime you see at least one, that's a clue. It's faster, or at least easier, to solve this by the complement instead of finding the probability that you get 1, 2, 3, or all 4 of the mediums out of the first 4 you draw. That's a lot of work. So let's do the complement. Which is the probability. We're going to find the probability that you don't find any mediums in the first 4, then subtract it from 1. That'll give us a likelihood that you get at least 1. So no mediums would be 16 out of 20, and we're going to do that for 4, so that'd be 15 out of 19, etc., etc., etc. Did we already do that one? That sounds familiar. But anyway, we can go up here and change those. So it would be 16 times 15 times 14 times 13. Okay, that's the same, so no big deal. And then math, convert to a decimal. All right, so remember that's what we're subtracting from 1. So that's a probability that we don't get any at all. We have to subtract that from 1, which will leave us the actual complement, which would be, that is a complement, which will leave us with 62.4% chance. So there's a 62.4% chance that you'll find at least one medium by the fourth one that you check. All right, given the contingency table for probabilities of adult American males, find the following. So high cholesterol and blood pressure. So this contingency table between high cholesterol and high blood pressure. So it looks like 11% of adult American males have both high blood pressure and high cholesterol. And then you can see the others. First thing you might want to do is fill in the margins. So overall high cholesterol, that looks like that's going to be 32%, and then 68%. And the bottom's always 1, in case you're curious, the bottom right. Adding those two together, we get 73%, and then here we have 27%. So what's the probability that a man has both conditions? Well, that would be high blood pressure and high cholesterol, which would be 11%. That was easy. High blood pressure, so overall high blood pressure, whether or not they had cholesterol, we're just collapsing those two for the marginal, which would be 27. Our probability a man has high blood pressure if it's known he has high cholesterol. So out of those with high cholesterol, which is the 32%, what's the probability they have both? 11%. So 11 out of 32%, which will give you 34% overall. Are the two events independent? Well, again, we need to compare a conditional to a marginal. We already have our conditional, which is probability of high blood pressure given cholesterol. So we need to compare that to the overall marginal distribution of high blood pressure. So high blood pressure's marginal distribution, we said, was 27%. And how does that compare to the 34? Well, it's less. Is that far enough, or depends on the sample size to see if that's... It is significant, but whether or not statistically significant would depend on the sample size, right? We'll get into that stuff kind of later with inference and hypothesis testing. But I would say that this is a significant increase. So your probability of having high blood pressure goes from 27% for the general population. If you have high cholesterol, it actually increases. Those two are actually linked together, is what we're trying to say. So are the two events independent? No, because the conditional probability is 34%, where the overall probability, the marginal, is 27. Those are not the same. Number 12, this is the last one that I'll be doing with you guys. Suppose a U.S. resident, suppose for a U.S. resident, the probability of a U.S. resident has traveled to Canada is 18%, and to Mexico is 9%, and for both countries is 4%. So we have 18 is the marginal for Canada, 9% for marginal for Mexico, and 4% is the intersection of both. So if we subtract those two, they'll give us 14% of that have only been to Canada, and 5% that have only been to Mexico. The first one we want to do after filling in the diagram is what's the probability someone has traveled to either country. So we can use our rule, our general rule, addition rule. So 18% plus 9%, we subtract the 4% because it was overlapped. The overlap was counted twice, so we got to subtract it once. When we do that, we'll end up with 23%, I believe, yep. What's the probability that someone who's traveled to Mexico has visited Canada as well? So of the people who visited Mexico, which is 9%, that's our new denominator. That's the only ones we're interested in. 4% had been to Canada as well, so 4 out of 9% would give you 44%. Are they two disjoint events? No, because there's an intersection, right? The intersection is not empty. So the intersection of having been to Mexico and Canada is 4%, which is not equal to 0. Are they independent? Well, we already have our conditional distribution of probability of going to, having been to Canada if you've been to Mexico as well. We need to compare that to the overall of being to Canada, which was 18%, and 18% is not the same as the 44%. So if you've been to Mexico, your chances of going to Canada as well is much higher than the general population. So those are not independent events. And that's it. So if you guys have any questions, just let me know, and I'll see you later.